Let me guess a situation you have seen before. A Spark job is running slow. Someone says add more executors. You add more executors and the job is still slow. At this point, we start blaming Spark, the cluster, the cloud provider, and the universe. But in real projects, the problem is much simpler. Your partitions are wrong. Today, I will show you why partitions in Spark are often the real reason your jobs are slow. Hello everyone, welcome to Big Data Factory. In this video, we will go through this like a performance clinic. We will go through like what partitions really are in Spark, and after that how under partitioning and over partitioning both slow you down, and repartitioning versus coalesce and when each makes sense, how partitions interact with shuffle, and finally a simple decision checklist you can use in real jobs. By the end, you should be able to look at a slow job and ask, is this a code problem or just a partition problem? So what is partition? In Spark terms, a partition is just like a chunk of data. Each partition is processed by one task on one core at a time. So partition control parallelism. If you have 8 cores and only 4 partitions, then at any moment only 4 cores are doing work. Half your cluster is basically on a coffee break. On the other side, if you have 8 cores and 50,000 tiny partitions, now Spark is spending a lot of time managing tasks, doing scheduling overhead, and not actually doing useful work. So the goal is not as many partitions as possible, not as few partitions as possible, but the right number with the right data distribution. In code, you can quickly inspect partitions. For example, if you have a data frame df, you can check how many partitions its underlying RDD has. Using simple Python script, get num partitions. And for shuffle operations like joins and group by, Spark uses shuffle partitions. Many Spark deployments still default this to something like 200. That's not always wrong, but it's definitely not always right. We will come back to shuffle partitions in a bit. First, let's talk about under partitioning. If you have ever seen a job where CPU usage is low, the job feels slow, but nothing seems overloaded, you might simply not have enough partitions. For example, you have got a big data set with 100 million rows, and after some operations, it ends up with say 4 or 8 partitions on a 20 core cluster. Spark will happily run it, but only a few tasks are active. Many cores are idle, and you sit there thinking the cluster is weak. In reality, the cluster is just waiting for more work. A classic example is shown in the screen. In this case, adding reasonable parallelism with repartition can help. And after adding repartition, now you get more tasks, more cores are busy, and the stage finishes faster. Now the opposite, over partitioning. Sometimes people see repartition of 200 and think, 200 is good, so 2000 must be better, let's do 20,000. This usually leads to tons of tiny tasks, extra scheduling overhead, more task startup or teardown, more shuffled metadata. And suddenly your job is not CPU bound, it's overhead bound. You might see lots of very small tasks, a stage that looks busy in the UI, but overall throughput is disappointing. So here's the principle. More partitions help until they don't. After a point, you're just burning time in overhead. Even if the number of partitions is okay, choosing the wrong key can cause problems. If you repartition or write data like this, df.repartition of country, and in your data 70% of the rows have country is equal to US, then one partition will be much larger than the rest. That's a data skew, and it shows up as 1 or 2 tasks taking forever, everything else finish it quickly. This is why partitioning strategy is not just a performance tweak, it's directly tied to skew, shuffle, and how stable your jobs are in production. Now the classic interview and real life question, when do you use repartitioning versus coalesce? So coming to repartition, so we use repartition to increase or decrease partitions, and it always involves a shuffle. It is good when you want to redistribute data more evenly, and you use repartition either before a join or a group by on a key. Coming to coalesce, it typically uses it to reduce partitions. It tries to avoid a full shuffle. It is good near the end of a pipeline when you are writing out fewer files. So one pattern is use repartition before heavy operations to improve distribution, and use coalesce after heavy operations to reduce partitions of files without adding more shuffle. What I try to avoid is chain of random repartition calls or repartition of 5000 without understanding why. Every repartition is more shuffle, more data movement, and more cost. Partitions really start to matter when shuffle enters the picture. Any operation that requires data to be grouped or aligned by key, joins grouped by distinct certain window operations, will trigger a shuffle. Spark uses shuffle partitions for that. That means even if your source data is nicely partitioned, a wide transformation can completely change the partitioning layout. Common patterns I see: shuffle partitions left at default while data and clusters scale massively. 200 shuffle partitions on terabytes of data is under partitioning, and 2000 shuffle partitions on tiny data is overhead. So Spark 3 AQE, adaptive query execution, can help adjust shuffle partitions at runtime, but it's not magic. You still want a sane starting point. And people often ask, okay, but what number should I use? There is no single perfect answer, but here is a simple mental model I like. Think about data size and cluster size together. You want enough partitions so all cores are busy, but not so many that each partition is just a tiny slice. A rough rule some teams use is aim for partitions where each partition is on the order of, say, tends to a couple hundred MB of data, and somewhere around a few times the number of cores for shuffle heavy stages. The exact number depends on how expensive your transformations are, whether your cluster is CPU bound, input output bound, or network bound, and what your SLS are. The key idea is partitions are a tuning knob you should think about, not just accept defaults forever. Now let's translate this into symptoms you can actually see in your job. Your partitions are probably off if stage is slow but CPU utilization is low, then it's too few partitions. You see thousands of super tiny tasks, then it's too many partitions. And one or two tasks are much slower than the rest, then you have a skew or wrong key. You see huge shuffle read or write with many tiny partitions, then it's over partitioning with heavy shuffle. Instead of just throwing more executors at it, it's worth asking, do I need to repartition by a better key? Do I need more partitions for this stage? Do I need fewer partitions at the end? Is my shuffle partition config stuck at a bad default? Here is a simple checklist you can use the next time a Spark job is slow. First, check Spark UI. Check whether are all tasks similar in duration or is one much slower, possibly skew. Number 2, check number of partitions using getNum partitions and check are you clearly underusing cores. And number 3, before heavy joins or group by, consider repartitioning by key to improve distribution. And number 4, after heavy work before writing, consider coalesce to reduce small files without extra shuffle. And number 5, for shuffle heavy workloads, review the partitions. Don't blindly accept the default for all workloads. If you treat partitions as a first-class tuning tool, a lot of Spark key slow complaints become much easier to debug. If this gave you a clearer way to think about partitions in Spark, hit like and subscribe. I am posting 2 Spark videos per week focused on real production problems, not just theory. Now I'm curious, comment partitions and tell me, have you mostly ran into too few partitions, too many, or skew because of a bad partitioning key? Your answers will help me decide which partition topic to go deeper into next. Now we have a full video just on choosing partition keys or tuning shuffle partitions. And we'll meet in the next video. Till then, bye bye.